Hello, everyone, and welcome to AMAT 611. If I've never met you before, my name is Professor Zralowitz. You can just call me Joshua. Um, and so let me just quickly go over the syllabus for AMAT 611. So this is going to be a course on the basics of functional analysis. The prerequisites for this course are 510A, which is basic Lebesgue measure and integration theory, and realistically 513A, basic complex analysis. We really won't use either that much. It's really more important to have a certain level of mathematical maturity and to certainly have mastered the various techniques in AMAT 511 basic analysis. You absolutely need to master concepts like epsilon delta proofs, continuity, uniform continuity, convergence of functions, uniform convergence, et cetera, et cetera. The complex analysis will mostly be incorporated into the examples, which I'll go over. So I'll get more to that in a second. So the lectures will be posted on YouTube, and if you click here, this will take you to the channel for this course. I will be making lectures using my digital pen and pad. Okay. Well, I should probably delete this. It's not very relevant to where my office is, but my email is j last name@albany.edu. The office hours are going to be when the class is normally scheduled, 10:30 to 11:30. This is the meeting ID and passcode. I'm very flexible with when I can meet, so if these times are not good, or if I'm busy with other students, I'm teaching a course on the theory of interest for actuary and economic students with 60 students. So I might get busy. You just shoot me an email and I'd be more than happy to set up an appointment where we can meet on Zoom. Again, I'm very, very flexible. So the textbook is Elementary Functional Analysis by Barbara McClure. So you can get it fairly cheap on Amazon, and I think it's an excellent textbook, even just to have as a reference, because it's probably the most readable yet deep functional analysis book I've ever encountered. So I personally love it. Grades will just be based on assigned homework. Every week or two, I'll give homework. I'll be pretty flexible on when you hand it in, but it should be, you should probably be able to do it in a week. And I'll have a final problem set where I'll probably make you just present some problems to me via Zoom. Right. So the topics we'll cover are chapters 1 through 5. I might go slower if need be. So let's just go to the table of contents. So it's pretty standard topics. I'll talk about Hilbert spaces, the very basics of operators on Hilbert spaces and Banach spaces. Of course, I'll talk about Banach spaces in the first chapter. I'll talk about the big three: Hahn-Banach theorem, principle of uniform boundedness, open mapping, and closed graph theorems. So at the very least, I will absolutely cover the first 3 chapters. I'm going to try and cover 4 and 5, compact operators, and the basics of Banach and C-star algebras. So even if you're not so much interested in pure math, I think Banach algebras are C-star algebra. The basics of Banach and C-star algebras are important, if for no other reason than that's really the easiest and clearest way to prove the spectral theorem and to discuss spectral measures, which pop up in, I'm sure there's machine learning papers that, deal with spectral measures, but I could be wrong. But anyway, okay. So a little bit more about the topics. So a lot of the examples will be drawn from particularly uh, Hilbert spaces of holomorphic Hilbert or Banach spaces of holomorphic functions. Barbara McClure is a uh, operator theorist who often uses in her research Hilbert spaces of Hilbert spaces of holomorphic functions. So in this book, there's a lot of examples on, the Bergman space, the Hardy space, the Fock space, and whatnot. I'll talk about, in general, reproducing kernel Hilbert spaces. I'll talk about the L2 theory of Fourier series. And because I have at least two machine learning people in this course, if I have time, I'll try to actually explicitly describe the Gaussian reproducing kernel Hilbert space, which if if people in real life use kernel methods for for SVM or support vector machines or whatever whatever they want to use, it's often they're going to use the Gaussian kernel, and in practice you really don't necessarily care what the actual Gaussian reproducing kernel Hilbert space is, but if you want to theoretically get statistical bounds for this reproducing kernel Hilbert space, it's very useful and it's very classical to actually describe it. And it's basically a Fock space, if you know what that is. And yeah, so I don't know if I'll have time to do that, but yeah. And just in general about this course, we do offer, usually taught by Professor Stessen, a more practical oriented, machine learning oriented functional analysis course. This is much more theoretical and proof based. And this course is really designed to give everyone a very strong foundation for actually using functional analysis and proofs, whatever kind of, in whatever research endeavor you choose, whether it's operator theory on function spaces, partial differential equations, maybe theoretical aspects of machine learning, whatever. And certainly one aspect of machine learning that you probably would need the material I'm talking about, which has seen some little flurry of popularity, is reproducing kernel Banach spaces. In particular, you want to do kind of like an L1 reproducing kernel Banach spaces, because L1, if this means anything to you, often gives you, when you do optimization with L1, lasso optimization, that gives you sparsity. Certainly there's a lot of functional analysis to even begin to read any of the papers on L1 in general reproducing kernel Banach spaces. Probably really you need more functional analysis than what we'll talk about in this course, to be honest. I've seen some of the papers and it's pretty heavy duty math. Anyway, so hopefully this was useful, and yeah, so long, take care. I'll put up the first lecture in the next few days, and yeah, so long, take care, stay safe. Hopefully I'll see all of you soon on Zoom.